This week we're going to look at 6.1, which is angle measure. And this chapter has, or this section has a lot of little things in it, but they're all relatively simple. So first thing, we're just going to switch between degrees and radians and degrees. So this little blue box, this is in your textbook, and it just tells you how this works. So the main two things you're going to look at would be, what says 1 and 2 here. So number 1, to convert degrees to radians, multiply by pi over 180. To convert radians to degrees, multiply by 180 over pi. So that's all we do to convert between the two. And let's go ahead and try that. So first one for A, it says pi. So if it doesn't have a degree symbol, the little circle, then it is assumed to be in degrees. Radians. So if it doesn't have the circle, it's in radians. So these are all in radians, and we're going to put them in degrees. So what we do is take what we're given, which is pi, and we multiply that by, from radians to degrees, we multiply by 180 over pi, and we get 180 degrees. To go from pi over 3 to degrees, we convert that by multiplying by 180 over pi. Cancel the pi. Then you have 180 over 3, which is 60 degrees. Next, pi over 6 multiplied by 180 over pi. Notice I'm drawing my little circle. I actually think it's a mistake in this textbook up here where they don't have the circle, because otherwise there's no unit there. So the degrees is a unit measure. So cancel our pi. 180 over 6 is 30 degrees. So these are really straightforward when you're just converting. You're just multiplying by either 180 over pi or pi over 180. So let's go the other way. These are in degrees. So we're going to convert to radians. So the first one would be 45 degrees times pi over 180. Okay, so this would be 45 divided by 180 is 1/4. So this is pi over 4. 175 degrees to radians, multiply by pi over 180. And we will get 35 pi over 36. And then 270. Okay, 270 divided by 180 is 3 pi over 2. Okay, so those are really quick problems. There's several of those in the assignment. So next we have angle measure and standard position. So in chapter 5, we already talked about this. Angles are measured from the positive x-axis spinning around counterclockwise. So in these 4 diagrams, we have 4 different angles represented, and they're just an assortment of angles. Sometimes you have to spin around more if your angle is over 360. And what this brings us to, though, is coterminal angles. So angles are coterminal if their sides coincide. So coterminal means that the angle terminates at the same place for both of the angles. So in these diagrams, you can see that angle A and angle C, those both terminate at the same place, even though they are, A is a smaller angle than angle C, it still terminates the same place. So what this means is that you're adding 360 degrees to A, and that would land you at C, which would mean those two angles are coterminal. So this works better through examples, so let's just go into those. Okay, so we're going to find some angles that are coterminal with 30 degrees in standard position. And so we're just adding or subtracting multiples of 360. So if we take 30 and add 360, we would get 390. So that would be an angle that is coterminal with 30 degrees. So we could add 2 times 360, 5 times 360. We could subtract those numbers and come up with other angles like that. For the next one, it says find angles that are coterminal with theta equals pi over 3 in standard position. So this is similar, except we add or subtract multiples of 2 pi. So if we do that, we would get pi over 3 plus 2 pi would be, if I convert that to, convert the fraction, it's 6 pi over 3. So an angle that would be coterminal with pi over 3 would be 7 pi over 3. So we're just adding and subtracting multiples of 2 pi or 360. Okay, so let's clear this out. So this says find an angle that is coterminal with 1250 degrees between 0 and 360. So just like the other problem, we're going to, in this case, subtract multiples of 360 from 1250. So I know that 3 times 360 is 1080. So 1080 is a multiple of 360. And from that, I would get an angle of 170 degrees, which is between 0 and 360. So the questions, they can't get too complicated with these. Okay, next we're going to look at arc length. So arc length is the formula S equals theta r, and that's just the length of an arc across from an angle. So the diagram shows a circle and a portion of that circle in pink. And so S, which is the, it's a piece of the circumference, this is the arc length. So for this problem, for any of the problems that are arc length or area of a sector, theta must be in radians. So for the A part, it says find the length of an arc of a circle with radius 10 that subtends a central angle of 30 degrees. So I'm using the arc length formula. Very straightforward here. This tells us that the radius is 10 and the angle is 30 degrees. So I'm going to convert that to radians, which is pi over 6. So the arc length is 5 pi over 3, and that would be in meters. For B, it has us solve for something else. So it says a central angle theta in a circle of radius 4 is subtended by an arc of length 6 meters. Find the measure of theta in radians. So this one is giving us the arc length, which is 6, and the radius is 4, and we're solving for theta. So theta would be 3 over 2 radians. Okay, area of a sector is very similar. This is derived from the area of a circle. And so this is just finding, chunks, pizza-shaped chunks of a circle. It says find the area of a circle with central angle 60 degrees if the radius of the circle is 3 meters. So the area formula is 1/2 r squared theta, and theta has to be in radians. So it's 60 degrees here, which is pi over 3. So the area of the sector would be 1/2 times the radius of 3 squared times pi over 3. And so the area would be 9 pi over 6 or 3 pi over 2 meters squared. So with this problem, just like the arc length problem, it might give you the area and have you solve for theta or the radius. It just depends on what the problem is. So just make sure to read those. So now we're going to look at linear speed and angular speed. Suppose a point moves along a circle of radius r, and the ray from the center of the circle to the point traverses theta radians in time t. Let s equals r theta be the distance the point travels in time t. Then the speed of the object is given by, and it gives you our two formulas here. Angular speed is omega equals theta over time, and linear speed is v equals s over t. And it tells you in that problem that s is r theta. So I like to rewrite linear speed as r theta over time. And your book does do that in the next problem, but it works easier to have that knowledge here. So let's do our problem here. A boy rotates a stone in a 3-foot long sling at the rate of 15 revolutions every 10 seconds. Find the angular and linear velocities of the stone. So I will draw a little circle here just to represent. So this would be an bird's eye view. So you have a circle. The boy would represent the center, and then the sling is 3 feet long. So this is giving us so the sling length would be the radius. So that's a very simplified diagram of this picture. I actually don't think they help too much in these problems, but it might. So let's find the angular velocity, which is omega equals theta over time. So what you're going to ask, or what I would ask a lot in these questions is, what's theta? Well, we're talking about a circle. So 1 revolution of theta, or 1 revolution around the circle would be 2 pi. Okay, and in this problem it says that happens 15 times every 10 seconds. And just remember the numerator of this is in radians. So we would have 2 pi, that's 1 revolution, times 15, because that's how many revolutions it says. So, and it does that in 10 seconds. So it would be 2 pi times 15 divided by 10. And that would give us 3 pi radians every second. Okay, so that's angular speed. Now for linear speed, so our formula given, or the one I adjusted, is r theta over time. And you'll see really quickly why I use r theta over time versus what they tell you to use. So the radius, we just fill that in. That's easy. Well, the radius is 3. Theta, if it went through that 1 revolution, that would be 2 pi. But it tells us it does this 15 times. And then it says it does it every 10 seconds. Okay, so just you have to remember this is in seconds in the denominator and this is in feet in the numerator. And it's in feet because we have introduced the length 3. So our units would be feet per second. Because we're not talking about the angle itself. And then we just simplify this. This would be 9 pi feet per second. And if you just kind of analyze this, what we have there, it's 3 times 2 pi times 15. If you look at 2 pi times 3, that's really just the circumference of the circle. So 2 pi times 3 would be 1 revolution, but it would throw in that measurement of feet. And then it does that 15 times, which makes sense. So it's the circumference of the circle multiplied by the number of times you go around that circle. Okay, so this is the relationship between linear and angular speed. So if a point moves along a circle of radius r with angular speed omega, then its linear speed v is given by v equals r omega. So I'm going to go back to this previous page and just keep in mind again that omega is theta over time. So I'm going to go now back and let's adjust this formula too. So this is really r times omega over time. Okay, which is really what I had. That's really s over t. And the reason, again, why I used it on the last problem is because it's so much easier and it makes sense to me to use it like that. So here it is introduced. It just isn't clearly introduced. So let's look here. A woman is riding a bicycle whose wheels are 26 inches in diameter. if the wheels, I'm going to stop there and just say, remember, we're using radius, so the R would be 13 if they're 26 in diameter. So if the wheels rotate at 125 revolutions per minute, find the speed at which she is traveling in miles per hour. So just a hint, if you're doing any kind of motion problem and like somebody's riding a bike and it's going 3,000 miles an hour at the end, just check your work because you're probably wrong because most of these work out to be realistic. Okay, so this is angular speed. And I'm going to use V equals R theta. Oh, finding linear speed from angular speed, sorry. R theta over time is my linear speed. And let's just work through this. So in this case, R is 13. Omega is 125 times 2 pi. So it's 1 revolution times 125 of those. And so V is going to equal 13 times 125 times 2 pi. And I don't have a denominator here because it's just 1, so you could put this over 1. And so V equals, if I multiply that all out, it's 3250 pi. And this is, the wheel was 13 inches, the radius was 13 inches, so this is inches per minute. And so this would be inches per minute. Put those units up there. And so it's 3,250 pi inches per minute. That's not what the question is asking you to find. So it says find the speed at which she is traveling in miles per hour. So we have to put this into miles per hour. So the conversion for these problems is really the most complicated part. And so let's just go through that conversion. Convert. Okay, so I always set these up in the same way. I keep it really orderly. So if I multiply 3250 pi, it comes out to 10,210 inches every 1 minute. Okay, and now let's deal with the time first. So if I multiply this by 60 minutes over 1 hour, then my time unit's taken care of. And now let's deal from inches to feet. So whatever you're wanting to cancel out, you put in the opposite space, either the numerator or denominator. So I need to cancel inches. So there are, in 1 foot, there are 12 inches. And 1 mile has 5,280 feet. And so if we multiply that all out and cancel units, it'll give us the correct thing. So let's see here. Cancel minutes, inches, feet. And so now we're just left with miles per hour. So if I do all of that, this comes out to approximately 9.66 miles per hour, which is not very fast, but is a realistic speed for a bike.